this was the model we discussed last time. Dynamic Nelson-Siegel model, where we have observation equation here, and this part is the this one, right? This one is something else. So let's worry this one first. Okay. So when you actually run this program in GAUSS, first problem you might encounter is to start to find some startup value for x, okay, which is unknown. We'll get to that. But let's take a closer look at the dimensional problem, because we have 1, 2, 3. So we have 3 vectors. So dimension of x is 3. Okay, and of course this covariance matrix. This one is also 3 by 3 with variances on the main diagonal, and this one has covariance, which has variances on the main diagonal, but the number of those, the dimension of this covariance matrix will be the same as this one. Okay, so let's try to trace the problem. Using this program. Okay, so data here, it has a monthly frequency, and total number of observations is 99, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 maturities. Let's take a look at the data set, GBDNS, this one. So it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 maturities, right? But the first one is the day index. And it goes all the way down to 99. Okay. So 99. So you are reading this text file, which has dimension 99 by 13, right? Including index, time index, right? We try to make the monthly spot rate in decimal. These are in percent, right? So we divide these by 100. So that is done here. You see that 1 through cap T. So all data, but we start from first column to 13th column, right? And then T, of course, number of observation, because sometimes you could start with, let's say, from 15th. So you're working with a subsample, right? You could work subsample. So if you redefine the sample, then you calculate number of observation again, right? Using function rows. It returns number of rows. Okay. Don't worry about the rest. These are to store some intermediate variables. Then, because you have to initialize this problem, because you have coefficient pi, which has 3 numbers on the main diagonal, right? So you have the 3 numbers as 3 parameters to be estimated. Also, in a factor, you have to estimate 3 standard deviation or variance. Okay? And 3 mean parameters and lambda. And this one, 12 of them, this one's function will return n by 1 vector of ones. 1, 1, 1, 1. Okay? So 12 by 1 multiplied by 0.03, some small number. And because all these numbers are in vector, so I can stack it 1 by 1, right? I'm stacking it. Right? So this is your initial guess. Well, how to find those numbers? Well, it's wild guess. It's wild guess. Or if you prefer, if you count how many parameters to be estimated, 1, 2, 3, 4, 5, all the way up to here, then you can just put your initial guess. So this is the number of parameters to be estimated. But if you start with this curly braces and without this, when you define BB in this way, this will be row vector. But we define it column vector, right? So we transpose it this way. Okay. So if I block from here to there, then this is going to be your initial guess, right? Initial guess. Here's another way of initializing thing. I save something that looked like this one, BB, under this name. So when I say here GB DNS equals to BB, then this number, right? And then save GB underscore DNS. If I hit enter, then this is going to be saved in the current working directory with a file extension FMT. But you don't have to worry about it. But when you save it, and you can load it, load that matrix name. Okay? And then put it back, right? And then go on. The reason why I do this is I started my career at University of Alabama, and they have severe thunderstorm during summer. Always very severe, sometimes tornado. So accidentally, when I run this program for, let's say, almost a week, and if storm hits, then power is out, and all output is gone, because your wild guess is evaluated until you find some converging estimate, right? So it's very close there, running 6 days, 7 days, and then it's gone. So you have to start it again, wishing luck. Okay. So what I thought is, I try to save the latest combination it's been searching. So when power is out and it'll come back, then I can start from where I left. Okay. The way I do it is from here. So when you try to evaluate your objective function, you see when I receive this B, I define it as this one, and I save. Okay. So if it stops right here, then I can start from there, right? Because at that time, computer was very slow. So typically, if you have a big dimension job with many repetition, it takes ever. It takes ever. So that was my old habit here. Okay, so you start with those initial guesses or something like this one, and then this is the way we call optimum. This is optimum. What it does is try to maximize objective function numerically, given initial parameter and your objective function. So this is the name of your objective function, and it starts with ampersand. So this is their language. Okay. So you put optimum, parentheses, ampersand, and the name, and this, BB. Okay. Whatever the name, the same name. Okay. When it's done, it will return 4 output under this name. These are my arbitrary name. You can say x1, x2, x3, x4 if you prefer. Okay. This one is a coefficient. This one is a coefficient at maximum or minimum, because this is actually minimize this function. Okay. So you return a minimized value, and this is the function value at this parameter. Okay. And this is the gradient, and gradient is simply the first derivative of this one with respect to these parameters. We know that when you find minimum and take the derivative at the minimum converging parameter, then the slope has to be 0, right? First derivative has to be 0. So when you have those numbers, then it will return those first derivatives evaluated at this parameter, so same dimension. So you try to check whether, in fact, gradients are very close to being 0. Okay. Sometimes, if your problem is ill-specified, not well-specified, then you might find it difficult to find actual minimum, right? So if your function looks like this, very difficult to find minimum, right? So in that case, this value will not be close to being 0, although it converges. Okay. This one returns number 0 to other up to 10 something. If return code is 0, then you had no problem implementing your optimizer. And if you receive other return code, 1, 2, 3, 4, then you have to go back to check their manual, see what was the problem. Okay. So usually you expect this value to be 0 when it's completed without any problem. And then this is Gauss function. We can call it. And if you type call OPT-PRT, and then this one, then it will print on a screen that is more readable form. Okay. I'll get back to this part later. Okay. Now, this is the first 3 coefficients are corresponding to coefficient, AR1 coefficient. Okay, 3 numbers. And supposedly they are expected to be bounded from 1 to -1, right? 1 to -1. But some number exceeding that, right? So last time what I mentioned was we try to transform this one to, by using logistic function, we can transform these numbers bounded to certain range. For instance, 1 to 0. Okay. We know that from previous studies that the coefficients are close to being 1, not actually being 1. So we confine this one from 0 to 1. Okay. So if you actually run this program, I don't know whether this will converge or not because I played a little with this one. So let me type here B and BB, because dimensions are same, right? The 1 enter as B is transformed, right? So I'm trying to print this one and print this one at the same time. Okay. We are concatenating these two vectors, right? When dimensions are the same, then we can concatenate, okay? And let's stop right here and see what happens. See that? This was your initial guess, right? This is transformed. And as you can see, these three numbers are bounded from 1 to 0, right? 1 to 0. How we did that? How we did that? Here. First 1, 2, 3 numbers. Upper bound, low bound, medium bound. So 1, 0, 0, 0. And these are original. Right? So you are trying to start with these numbers, but program will calculate your objective function using this one, transformed. Okay. Some others, like these numbers, standard deviation, this is element by element operations. So next three standard deviations are transformed to the variance, right? Variance. Because we will be using this variance to make. So let's say this is covariance matrix, and all others are 0, and we have 3 numbers, right? All variances. Sigma alpha squared, sigma beta squared, sigma gamma squared. The first factor, second factor, third factor, and their variances, right? So squared it, and this one is copied here, right? But the thing is, well, when you actually calculate this variance, when you look at the variance figure after your after the program converge, you will find usually this variance are some number very small, right? So something like this one. Okay. And we know that pi's, AR1 coefficients, they are like 0.92, 0.93, something, right? So scales are very different, right? So when these scales are very different, then because this is a numerical optimization, this may not work. Right? And in the worst case, if the variance is something like this one, scales are very different. Right? Usually, the way we calculate let's say, and calculate this one, first derivative. What is small change? Small change is, let's say, pi current value is 0.92, and delta pi, the small change is, let's say, 0.0001. So if this change, so 0.9201, and we use this one, we try to see if what is the value of this one at this number, and the value of f at this plus that, small change, and then compare, right? That's numerical derivative, right? Well, this is, small change, right? But if your parameter has about this scale, 0.0001 is big change, right? Big change. So to make it operational, I divide that by this number. This number. So making this one. So what I do is I put this as initial guess, and this transformation function will make it back to this number. Right? So what I like to do is either like to work with this number and that number, about this scale. Of course, it may work if you divide this one by not 10,000. Instead, you can divide it by 10,000, and it may work, but it may not work as well. So this is kind of magic number you have to learn from making mistakes, trial and errors thing. So actually, this was a very big thing in this kind of model. Okay, and then I believe 10th parameter is lambda in the model, and I want to make it positive, so this one. And then we have 12 elements in the vector of spot rates. So it has a 12 by 1 error vector, and it has variance, right? So this is going to be their variances. But again, the variance is going to be very small number. So I have to make it big to make, this thing operational, right? So this time I had to find more zeros to match scale. So without adjusting these two numbers, I guarantee that you won't be having any converging estimate from this model. Even if you don't divide it, the rest of the program may have no mistake, correct, 100%. But thing just one run just stops and collapses. Okay. And then you might wonder, well, I might have some mistake in my coding. In fact, coding is correct, but still you won't get to the converging estimate, okay, with these kind of small tricks. So it's worthwhile to take a look at those details here. Okay, where is, okay, so that's what I'm saying here. Those are variances, and this is true scale. very small number, right? I make it about this scale. So if you look at this column, scales are very similar, right? Very similar. Otherwise, you have very small numbers here, very small numbers there, and big numbers, relatively big numbers. So scale won't match. So that's first thing of this first trick you need to know. Okay, now then let's continue. Let's take a look at A matrix, is covariance matrix. This is coefficient matrix, covariance matrix of state variable, state vector, and this is covariance matrix of observation equation, or measurement equation. So let's take a look at the dimension of that. A, Q, and G. And let's stop there. Okay. So, matrix of coefficients, right? And their variances. And this is the variances as well. Right? So this one, okay, this one corresponds to this one. Okay. Now, let's go back to program. Okay, here, let me type what it does. P0 and P0 again. And let's take a look at X0. Okay, let's stop right there. So this P0 will be the initial P, and this is going to be initial X. Okay? So we expect this one being 3 by 1, this one being 3 by 3. Okay? But to make this one 3 by 3, I use this expression from the textbook, and dimension is 3. So this is identity matrix. So I minus A, we call this dot star dot as Kronecker delta. So we expand it using Kronecker delta, this one. And then this is back function using this Q. So if you define this, and if you know the dimension of the problem, then you can just simply copy it and calculate P first as a vector, and then using this P, you reshape it 3 by 3. Okay. So, and then this one, we use a mean value of a process X 3 by 1 there. So if you run this one, yeah, this is initial P0, and then you are reshaping this one as this one. So it's like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? This way. So reshape function is receiving this one as an input and then receive dimension. Then first it will start filling this 3 by 3 matrix starting from here. Okay. And then, right? And this is the initial guess on X. state X. So initial guess on state X, 3 numbers, and initial guess on this P was 3 by 3. Okay. And we define, what is this, let's see, what is this Z? Z is let me erase this part. This is our Z. Let's type D2. So H is this. This one. This one. Do you see that? This has dimension 12 by 1. So 12 ones, and then this one, and this one. Okay? So given lambda as an initial parameter, you are forming this one, and it will look like this one. And this is your x0. x0 was this, right? So if you multiply this by that, and that's your prediction. Z by that, right? So this one was 12 by 1, 12 by 3, 12 by 3, 3 by 1. So you can multiply it. So these are my initial guess. Okay. Next. By the way, D was I minus A times mu, right? I minus mu times pi, right? This part. This is in our notation D. So all is defined. So let's put this one as P and X here, P here, and then we can repeat this procedure. Okay? Probably you want to, because this is 3 by 1, so we expect this one 3 by 1. 3 by 1, 3 by 1, this, and 3 by 3, 3 by 1. So all dimension matches. Because it's 3 by 1, and this is its covariance matrix, so it has to be 3 by 3. So shall we take a look at PT? Let's take a look at X, XT, and PT. Okay. X is the one you initialized. So X, you want to take a look at what's the new value, predicted value, right? Predicted value, and their covariance. initial one is, this is the predicted value, and it's covariance. Covariance is, initially you have only terms in diagonal term, and these are or zeros, but that could be changed later on. These two did not change. The same thing, right? Why is that the same? So I typed x as an initial guess times a plus d. Oh, I know. Perhaps you may think that these are the same, but if you look at more digits, because our initial guess is something close being final estimate. So probably it won't be changing that much. Right? But how many forecast errors do you expect? This one is forecast error. What is the dimension of this one? Okay, your data look like this, right? 12 maturities and this many months, right? J counter run from up to all the way down. Okay? If J is particular number, it will pick row, right? It will pick row. And J comma dot means this row and all the numbers. Okay? And then that is transposed. So that number is transposed. Right? And then we know that H has dimension 12 times 3, 1, 1, 1, 1, right? And then slope and curvature, right? So 12 by 3. So this is 12 by 1. So 12 by 3, and x, we know that's 3 by 1. So 12 by 1, when you multiply it. So 12 by 1, and then subtracting 12 by 1. So this one has to be 12 by 1. And its covariance is this one. So it has to be 12 by 12. So let's take a look at here E and S. Error vector, its covariance. Okay? And those are fed in to this function, right? And that function is this one. Error vector and its covariance. So 1 over square root 2 pi to the power 12, because 12 is this multivariate normal distribution has 12 variables in it, so this number is 12. And determinant of covariance matrix, and this one. Okay. And actually, error vector transposed error vector and covariance inverse. But covariance has to be always symmetric, right? Symmetric. And also, because it's covariance matrix, it has to be positive definite, right? So instead of using IMV function to invert this one, we use IMV positive definiteness, IMV PD function. Right? So if in somehow you calculate HE as non-symmetric one, not positive definite, then you will probably get the error here. So we've seen that part. So when you do this, what is the dimension of this one? Your input has 12 by 1, dimension of 12 by 1, 12 by 12. What is the dimension of this number? If you put those numbers into this multivariate normal function, you're expecting single number, right? You have errors, error vector, right? 12 by 1. For simplicity, let's take a look at just these two. Bivariate normal. Okay? So if this works, then it has to work for that too, right? Well, how does multivariate normal distribution look like? Well, something like this. Okay? So if you put some number, some combination, this number and that number, let's say this number and that number, then it has probably some corresponding number, right? It will return this single number. If you put different numbers, then different value, right? So if you have dimension of 12, then more dimension, right? But you will get single number. See that? Hopefully. Single number, right? Single number. Okay, and because it's minimizing negative of log likelihood, so this is a likelihood value, this is a log likelihood value, and you want to minimize it, so I multiply that by -1. And each time this one go there and new one added, right? So ln likelihood value 1 minus ln likelihood value 2 all the way up to ln likelihood value at cap t. This is your negative of log likelihood function. So this is it. This is it. And I emphasized the other day that the most of the code here are reusable. You know, your problem may have different definition for A and Q and so on and so forth. If you simply estimating, let's say, 2-factor model instead of 3. So ignoring, let's say, curvature factor, the third factor, then the dimension is going to be shrink to 2 from 3, right? Then those adjustments has to be made. number of parameters, not 1 to 3, instead 1 to 2, and 3 to 4, and so on, right? So those are small differences. And then rest, mostly the same. Okay. Let's see if this problem actually runs. Let's get rid of this part, and let's see if it runs. So if it is right-click surface, now combination 1, 2 parameters constantly changing and evaluating likelihood function, right? It may take a while. These are current parameters, and these are first derivatives. So when you look at this kind of iterations, if these numbers get closer and closer to 0, then you can say, well, it's converging. If this number gets blown up, then probably you will see some big numbers and problem will blow up. But it looks like he's going somewhere. Okay. Here's a good part. Where is my, oh, right here. Did you see that? You want to see it again? That part was doing this one. If you're not so sure about what it does, then you can simply cut and paste and you can reuse it. But what I did was like this, starting from 1 through cap T. So starting from 1 through cap T. So if you are at time 1, then you have 12 numbers, right? 12 numbers. So 12 numbers could be like this, right? 12 numbers. Okay? And we estimated model. So 12 numbers, what I mean is at a particular time, let's say t equals to 1, I have 12 numbers, right? So this is it. Suppose you have all those converging estimates. And somehow you calculate this one, right? You have this one. The one I calculate is xt of t. So 1 and 1. 1 and 1. Okay? So if you have 3 values at time 1, so if you have 3 numbers for t11, so 3 numbers, you have estimate lambda, and tau is known maturities, right? So you can calculate what? Fitted value, right? Fitted value. So fitted value could be this. Well, it's off, right? Doesn't look that good. you probably, find some curve like this one, right? So if you have t and other t and so on, then you have different historical value and different fitted value, right? So what I did was, in this objective function, I calculate data fit. Data fit. What is fit? This one. This one. You see, this is data, and this was forecast, right? So this is forecast error. That's what I explained. But instead of using xt t minus 1, this is xt t minus 1, right? I can use this xt t, right? So h time xt t, and then I saved it. In this vector, I predefined, and then there. So I create data fit in this way, 99 by 12. And the first one, this fitted value is copied right there. The second iteration, copied another one. And then historical data, and this one is plotted, and t is running, right? So that's what you see from here. So let me copy this part, because things are in memory, so you should work. Control V. I hope so. Do you see that? So this is historical data, historical. And this is a fitted value. So when you looked at those fit over 1 through 99, there are some periods where there are some more gaps, right? Something like this one that is very close. But overall, it appears to be very good fit. Okay. So historically, if this fit is reasonable, this dotted line is reasonable, now you have a model. This one, okay? This is VAR. Then you can draw this one from multivariate normal, right? You draw numbers and calculate xt plus 1. T plus 1. Plug it in right there. And draw 12 numbers from this distribution. Add. Then this is going to be yt plus 1. Your prediction, right? You can continue and try it again. Try it again. Then what you get is whole term structure are simulated. Again, other path. Right? That's the way we simulate term structure using this model. So, model appears to be very simple, but lots of story behind, right? But when you fully understand the way this model is set up, and if you don't make mistake about the dimension in your programming, well, you have very decent model that can simulate whole term structure over time. What else? Right. The thing I didn't explain, don't worry about it. But here, let's see. There are many intermediate output you can generate. You see data 1, 0. You see data 1, 0 is the 1 through dimension. So J counter 1 through 99, J counter 1, 2, 3. Right? So it's storing X predicted value. One step ahead predicted value. You can store this one instead. If you're interested in alpha t, t. This is alpha t, t minus 1, right? So if you want to take a look at how these three factors look like over time, that's your answer. So let's take a look at that. I use xy function. I generate sequence. So it's x-axis 1, 1, t. T is 99, right? So you start from 1, increment by 1 up to 99. So 1 through 99 is created. The sequence is created, and you see data 10. So 3 series. Yep. First one. I think this is the second one. And the third one is somewhere here. Can't see it, but it's there, the third series. But if you compare this one with F1 sequence I provided in a EBIS work file, it will be very similar. Very similar. So these are unknown factor, 1, 2, and something going on here, third one, and those are these 3 sequences. So we started with something unknown, right? But we can make it visual. So once you have converging estimate, you can calculate this one using Kalman filter, right? Okay. Perhaps the last one could be, well, even if I distribute this program to you, and suppose you want to apply this one to your own problem, and accidentally you may have, let's say, 9 maturities, or sometimes you may have more, a fine frequency like 15 maturities. So dimension could get bigger or it could be smaller, right? But the number of factors are 3, the same. But because your data set is different and problem setup is slightly changed, somehow you need to find these magic numbers again. So you put some number. You know that after you do some experiment with trans function, if some number get close to 4.0, then it will be very close to being 9.9 something, 9.98, 9.99, 0.99, 0.98, something like that. And if it is something like 1.9, it is converted to like 0.75, something like that. So you can experiment. But other numbers, you have no idea. But if you played with this one with our KTB spot rates, then probably, because you have seen those converging estimates, you can make a guess that it could be something close to being that, right? But take a look at this part. So before I learned this combination, and luckily having this one, this is what I started with, hoping that works. Okay? So those numbers. How do I know those numbers? Well, I keep changing those combinations several times. Okay. Now, this one, it would be nice if you put any numbers here, and hopefully optimizer try to find a way. But that won't happen in practice. So sometimes, because you know that this number is going to be very small, so if you put more zeros here, then you may think that that would facilitate conversions, but sometimes it works the other way around. Sometimes just putting vector of ones, which has very different scale, may work better, even all tens. So you have to experiment it. But sooner or later, you can build some guess where when you actually see the repetition and collapse, then you can see that, well, particular set of parameters are not improving over iteration. Then, you keep those, and then those set of parameters that appears to be problematic, you change that part and see if whether that will help your problem. But even if you do that, still this particular problem had a very difficult, was very difficult to make it converge because of the initial guess, particularly this way. Slope. As I said, the sensitivity parameter to alpha t, level factor, was flat. And sensitivity factor for a slope factor was declining this way, right? And the third factor was this one, right? Curvature factor. So I indicated that this particular problem, there are some kind of overlap after some maturity between these two, second factor and third factor, right? So second factor is confused. So the parameter space for this one is very thin. So if you start from, let's say, suppose this is the right range. Suppose you start from here. Then instead of converging to this final estimate, you may go away or go away. It happens. Those parameters, it will find a way, usually. But this problem is very sensitive to this one. So as I mentioned, finding this number is key in practice. So how will you find this one? Well, you know how to calculate historical slope, long rate, short rate, right? So you calculate that using the data and take the average. Suppose that turned out to be, so long rate, short rate. So this distance is positive, right? This number is positive. So if you take historical slope and take the average, there will be a positive number, right? So you put that as an initial guess. But I don't know why, because those three are unknown factors. Instead of finding the factor, like this historical one, it finds, the second factor it finds is negative of second factor. So short minus long. So sign is reversed, right? So I believe that historical slope, when I calculated that, was about 0.028. And I tried that as an initial guess, and it fails. It fails. But I later found that in the repetition, iteration, you try to find some negative value for that, and then find no stable combination and collapse. So what I did was I put negative sign instead. I start from negative value, and then suddenly start working. Of course, and then collapse. And then later I found the problem lies still in the scale of this and the scale of this one. So in the trans function, I divide things by 1,000 or 10,000. So when everything is in right scale and right with right initial guesses, then magically start working. So even if you try this one with very similar data set, or even if you extend your sample from here to, let's say, here, this may or may not work. It's that sensitive. If you add, let's say, one more month, then probably what you can do is you change this one from 199 to 100, read them all, and try to read off the latest converging estimate as your initial guess, right? Then because you added only one line here, probably you don't expect any dramatic change in your parameter estimate, right? But in reality, it may not work. If not working, then you have to start searching for initial guess again, because it's very thin because of that problem. Local minimization problem. But that's a well-known problem of this type of model. So, okay. I've shown fitted value for x of t as previously this one, right? But in our program, you can calculate, you can retrieve this one as well, right? How about this one? This is your whole sample. So let's say you are at 50th, cap t is 99. You have more information, right, than this one or than this one. So as far as information is concerned, this is, let's say, accurate prediction. This is conditional expectation. So we will minimize mean square better. It's good. But this is better, right? Because this has more information. But suppose you have all the information, even if you are looking at this observation, suppose that you have all the information, then you can probably tell better, right? Something unclear could be better, could be more clear as this time develops, right? So we've seen how to calculate this kind of thing in terms of expectation formula. And from here to there, we used conditional expectation or bivariate system, right? there is an algorithm for this one too. So this is very similar to the previous one. See? A, Q, mu, lambda, G, right? All those similar. But there are something like this block, and when you do this one and this block, and then from here to that block. I was recycling this code from someplace else. So this part you don't have to worry about, but you need to, let's say, X predict is XTT. X update is XTT, right? So if you keep storing this one in right place and then form it this way and then rest, it will be automatic. Okay? So if you really into the estimation of this one, then this estimate is usually the best. And if you write a paper, professional paper, they will ask you this one. Then you have to have to use this type of smoother. But this beyond your undergraduate level. So let me skip the part. Okay, seen enough for the Kalman filter problem? You see? Very similar, right? The factors are very similar shape. So the one you couldn't see was probably this one. So model is, we started with this simple two set of equations, system of equations, right? And try to define what is alpha, what is z, what is y, and so on in a particular framework. Let me tell you that this is, in fact, very challenging problem. Not many graduate students would run this type of estimation problem. So if you understand what's going on, then probably you got good talent in econometrics. So for this particular problem, we know, in fact, with right programming, you can get all you want, right? Then if you have different problem that can be set up in this way, you can apply this one again. Okay? So we'll try to discuss some other applications so that, how to model things in this framework, state space model framework, when you have some problem that doesn't look obviously in this form. Okay? So we'll get to that part. Actually, this is a smoothing algorithm. So last block of code is this one. You can recursively predict this value. So we'll take a look at a couple of models. One known as Fed model, and the other one, another model called unobserved component model. And those are, handled quite easily in our framework. Okay, let me stop here. And do you have any question? How many of you applied for internship this time? 1, 2, 3, 4. Do you got the message? Email? So all selected. Haven't checked yet? We try. Yeah. We chose 21 senior students and same number, 21 students from junior. So this time 42. But I like those competition on TV, like Shusuke thing, those things. So the maximum number limit was like 40 that I announced. So 2 is going to be dropped by the end of practice course. So hopefully you don't get involved in that group, dropping group. Okay. Sorry that we had a technical difficulty at the outset. Hopefully you find it interesting, and if you need this code, then stop by. Okay. Thank you.